All right, I'm going to show you how I do controlled experiments with my simulations using this transformation experiments. And there's a couple of critical ideas I want to show you is like difference between a positive control and a negative control uh, in, a, in an experiment. Uh, Positive controls really you add something and then it has a result that you would expect. So it's like a positive indication. Um, you know, right here I have this non-resistant E. coli. I run an experiment and I would expect for it to grow. So I have this controlled experiment and yeah, it grows, right? Now the negative control is I get rid of that E. coli, I run my experiment, and since there's no E. coli around, I don't have any growth. So that's the difference between a positive control and a negative control. In both, it's exactly what I would expect. But I'm just running a comparison just to make sure that the thing that I'm manipulating is the thing that I want to be happening. So in this case, I want E. coli to grow, and it grows. And how do I know that this is the thing that's causing the growth? Well, that would be the positive control. I eliminate it, this would be the negative control. Okay, so number one, difference between positive and negative controls. Number two, critical experiments. And these are experiments that are really adjudicating between two mutually exclusive hypotheses or models. So uh, in this case, I have two models, actually really four models. I have two ways we'll be doing this. And thirdly, uh, just how does the chain of reasoning work? So oftentimes with lab experiments with students, I have them just run basically two experiments, a control group and an experimental group, and that's it. Then they run multiple trials of the control group and multiple trials of the experimental group, uh, if we're lucky. And then we just compare those two. And based on that, they're supposed to make some conclusion. But really, in science, you want to do many controlled experiments and then build a chain of reasoning from that. And so that's the kind of luxury of a virtual experiment or computer model like this is we can manipulate lots of different things and build a chain of reasoning based on this kind of model in a better way. So I have this document here, and I'll put this in the link. And so here we go. So first, we have this research hypothesis that non-resistant bacteria traits can be transformed into ampicillin-resistant bacteria traits. So we're taking non-resistant, transforming it into ampicillin-resistant. And we have two models here. We have model one, that this supernatant, which is going to be this like heat-killed substance that's going to have DNA, it's RNA, protein, basically the plug of bacteria. Uh, and in that supernatant, it can transform the traits of bacteria. And this is weird, but this is what Frederick Griffith discovered. It's called the transformation principle. And then in model two, we say traits are passed down only from other bacteria or maybe by mutations. Now, we have these two models, right? One that traits can be transformed from the supernatant, other that traits are just passed down from parent to offspring. And then we have common observations. And this is where a lot of I noticed experiments that I do are common observations that don't really adjudicate between two models. They just kind of show that one model is supported or rejected. And that's what a lot of science is. But what we really want are critical experiments where instead of having these common observations between two models, you have an experiment that is only going to be true if this model is the case, model one's the case, or only your results would indicate that model two is the case. And so that's what we're really looking for. Okay, so what I have here is a series of experiments that I'm going to walk students through. And I really will end up, when I have my students do this, I'm going to delete these columns, and they are going to predict the outcome. So for example, in this controlled experiment, negative control to test that ampicillin kills the non-resistant bacteria, and this is what they're going to add. So 100 milligrams of per milliliter of the non-resistant E. coli, no ampicillin, no supernatant. So they just run this experiment. But before they even open up the simulation, they're just going to make these predictable outcomes based on model 1 and predictable outcomes based on model 2. So what should be true, right? If this model's right, what should be true? If this model's right, what should be true? And so they'll fill in the table, it'll be something like this, and then we'll go over it. Then they're going to open up the simulation, and they're going to say, did it grow or did it not grow, right? Just did they see growth or not? So here is one of the things they're going to do is what happens to these non-resistant. Here's negative control, and then with ampicillin, well, it should kill it, right? And it does, okay? So we have that. Then we have a negative control to test that ampicillin-resistant bacteria can survive versus the positive control to test that ampicillin-resistant bacteria have traits that allow them to survive. So here we're going to use the non-resistant and the negative control, ampicillin-resistant and the positive control. So we already kind of did this first one, non-resistant. We run this, they all die. Now let's use ampicillin-resistant E. coli. This would be our positive control. If they're ampicillin-resistant, we add ampicillin and they should survive. And alas, they do, right? We get growth. Okay, good. Now, another one is to test negative control to test that heat-killed ampicillin-resistant supernatant passed traits to non-resistant E. coli. And so in this case, we are going to turn this off. We're going to keep our ampicillin, but we're going to add this heat-killed ampicillin-resistant supernatant. Just to give you an idea, what's going on here is you take basically this ampicillin-resistant E. coli, and you're going to heat kill it, destroy it, and then you're going to take its leftovers, and you're going to grow that with the non-resistant E. coli. Well, first, let's see. In our negative control, we're not going to add any non-resistant E. coli. We're just going to add ampicillin and the supernatant. And when we do that, let me go back up here. When we go here and run this, we get no growth, right? We killed it and nothing grew. So no big deal here. Well, in our positive experiment, or really this is our experimental group, is we're going to say, hey, will this transform this E. coli? And that's really what this model is saying, is model 1 is saying the supernatants, their traits are going to transform the traits of the non-resistant E. coli. Now, if we get a result here, it supports this model and rejects this, that it's just passed down in this way. It's not saying, what I'm saying here is it's not only this, it's this plus this. And what I mean there is in model 1, the bacteria can get traits both from their parents, both from random mutations, but they also can get it through this transformation principle. And so here in model 1, we would see growth, but if model 2 is right, we shouldn't see growth. So this is kind of that crucial or critical experiment. So here we go. And we make sure we add that. We run this and we get growth. So we get transformation. And it's coming up as ampicillin-resistant E. coli because this non-resistant E. coli that we added was being transformed by the supernatant. So what I would have students do is go through, they're going to complete these predictions, then they're going to go through and I'm going to have them explain the purpose of like experiment E, experiment F, like these two experiments. I give them guidance here of what are the purposes of some of these other experiments. I like to do that to scaffold them. So scaffold the kind of responses I'm looking for to help guide them towards answers that are valuable or that I see as valuable. And then which experiment is the critical experiment is what they're going to see. Then I'll stop, check their work, we'll discuss it, debrief, then we'll open up the simulation. From there, then they're going to fill out results from the simulation. So they're going to go through, gather data, collect data, and then from there, run each of the experiments, write the results of each experiment in the table, and then I go through and I talk about what a critical experiment is, and then I give them a example of what a good reasoning statement looks like. A lot of times my students think a conclusion should just be like one sentence. I want them to explicitly see what a chain of reasoning looks like. So here I gave them an example. Here's a chain of reasoning based on all those experiments. So rather than just using one experiment, one experiment to make a conclusion, using multiple experiments to make a conclusion, which then, alas, ends with, therefore, these experiments support model, and it's going to be 1. So they'll fill in the blank above. Then they'll go through and do the same thing with a different one, that DNA causes transformation, or is it protein and RNA that causes transformation? The way they'll do that is through another series of experiments to build a chain of reasoning, and they will either add, for example, they'll add catalase as like a control group. Catalase shouldn't do anything to the supernatant. They'll add RNase, see what happens, protease, see what happens to destroy proteins, or, ooh, this should say DNase to see what gets destroyed and what prevents transformation. They're going to go through basically the same thing, except in this case, they're going to make their own reasoned conclusion built on a chain of reasoning, like I showed them in the first set of experiments that we did. So I like to scaffold these things. So in this activity, I'm showing them differences between positive and negative control groups. So negative control group, positive control group, that you use multiple experiments to support a conclusion, and that there are critical experiments where you adjudicate between two hypotheses. So in this case, if there's growth here, it supports model 1. If there's no growth, it supports model 2. Or in this case, if there's no growth here, it supports model 1. If there is growth, it supports model 2. And these critical experiments with lots of controlled experiments is how we really build conclusions in science. All right, I hope that's helpful.